So welcome everyone to the afternoon plenary. I'm pleased to be the chair introducing Damien Rousson. Damien Rousson is a senior scientist and the group lead for the Computer Language and Systems Software, or CLASS group at Berkeley Lab. His early career focused on simulating turbulent flows in multi-phase quantum and MHD media. And he currently researches, develops, and teaches parallel programming models for high-performance computing and deep learning. He leads the development of the Caffeine and OpenCoRe's parallel runtime libraries for Fortran compilers, the Fiat's deep learning library, and the Matcha biological T-cell motility simulator. He also teaches tutorials on the UPC++ template library. He co-authored the textbook Scientific Software Design, the object-oriented way, and has taught related university courses and tutorials on Fortran 2018 and Agile software development. He's an alternate member of the Fortran Standards Committee and has held staff and faculty positions at the City University of New York, the University of Maryland, the University of Cyprus, the University of Bergen, and Stanford University, as well as staff and management positions at the U.S. Naval Research Lab and Sandia National Labs. He received a 2003-04 NASA Summer Faculty Fellowship and a 2020-21 Exascale Computing Project Better Scientific Software Fellowship. He founded and leads Archaeologic Incorporated and Sorcery Institute, holds a BS from Howard, an MS from PhD from Stanford, all in mechanical engineering. He's also a licensed professional engineer in the state of California. Please join me in welcoming Damien Rousson.
Thanks for the introduction. I guess I almost forgot I had done quite so many things, and I realized I don't have a microphone on me. But can people in the back hear me? No. So I guess I should step to here. Great. So the title of my talk, What Happens to a Dream Deferred? And it's all about chasing language-based parallel programming for HPC and AI. In addition to being at Berkeley Lab as of the beginning of this year, I'm also adjunct faculty at San Diego State University. So I wear way too many hats. Let's hope I can talk fast too. So first I want to take you on kind of a may seem meandering walking tour from software archaeology, which is the field of digging through old code, something I do a lot of, modernizing them to modern standards, and all the way to software modernity, and sort of what my dream has been for software development for science for a long time, and how that has played itself out in HPC and AI. And then I'll talk about some background matters that I'll explain when we get there, and conclude. So the title comes from a poem entitled Harlem, by Langston Hughes. He was a Harlem Renaissance poet. And in 1951, he wrote, "What happens to a dream deferred? Does it dry up like a raisin in the sun, or fester like a sore, and then run? Does it stink like rotten meat, or crust and sugar over like a syrupy sweet? Maybe it just sags like a heavy load. Or does it explode?" We'll come back to that theme. A few years later, John Backus led the team that developed Fortran. Most of my work is either in or supporting the Fortran programming language. This is a picture of the first Fortran manual from 1956. A few years later, Fortran was already playing a social justice role in the world. Those of you who saw the movie Hidden Figures might remember that there was a scene where one of the characters went to a library to check out a book on Fortran because she was a computer, back in the day when computer was a job title, not a machine. But they had finally brought in the digital computers to this group of mathematicians. This was a segregated era, so black women who were doing mathematical calculations for the space program. And since digital computers were coming along, if they wanted to keep their jobs, they had to learn how to program. So she went to the library, and I think they didn't want her to let her check the book out, so in a subversive act, she took it anyway. I find that inspirational. And fast forward to 1977, John Backus actually, over time, was moving away from Fortran, and in his Turing Award lecture, focused on a functional style and its algebra of programs. So it seems that was what was capturing his interest at the time, and maybe one of the reasons that he was beginning to move away from the language. I showed up on the scene not too long thereafter. Wrote my first Fortran program at age 12 at the Pinellas County Science Center, where I grew up in St. Petersburg, Florida. So that center played a big role in my life, and unfortunately was dormant for the last 5 years or so because they ran out of funding. So I'm really happy to say I just got a text message a couple of days ago from my brother, who's on the right, in the picture on the right, and he's a state senator in Florida and just was able to arrange $2.5 million to bring back the Science Center in St. Petersburg. Fast forward to the 1984 to 1991 era, and it's funny, just before this talk I got a call from Eugene Mia, who used to be at NASA Ames Research Center. He's now retired, and he introduced me to Jim McGraw, who at the time that I met him was at Lawrence Livermore National Laboratory. And just before I went to meet Jim for the first time, I decided to look up some of his work, and given what I just said about how central Fortran is in my career, you can imagine how excited I was to find out that one of the first things I pulled up was a technical report from 1991 that was actually going back and citing a debate from 1984 where they were debating whether or not to retire Fortran. Of course, it's an international standard, so I'm not sure exactly what that means. And Jim was on the side of retiring the language. So let's take a quick look at why. And so even by '84, it was clear by all indications that future supercomputers would be multiprocessors, that we would need parallel programming. And when they looked at some of the problems in Fortran at the time, or I guess first they looked at what would define for them the characteristics of a true parallel programming language. So one, the language must insulate the programmer from the underlying machine. Two, the parallelism must be implicit in the semantics of the language. And three, when a programmer desires determinacy, the language should provide it. So they were looking at the problems that Fortran presented at the time in terms of achieving that vision. They used an example of calling a function or two functions. So you have a statement A equals foo of x and B equals goo of y. And the key problem is that you can't know whether you can run those two statements in any order or in parallel if you don't know whether x might be an alias for y, right? So the big problem at the time was common blocks. Of course, you could do the same thing in other ways now, for example, with pointers. And so their solution for this was to develop a new functional programming language. So what they were saying is that functional programming languages, on the other hand, have all the requirements that they're looking for. A functional program is a collection of mathematically sound expressions comprised of both intrinsic and user-defined functions. These functions are well-defined and deterministic. So if you they have a unique mapping from inputs to outputs. If you give them an answer, an input, then they always give you the same output. And they should also have no side effects. Side effects are anything that modifies the computer state other than mapping from inputs to outputs using local data. So printing to a screen or to a file, even halting execution, which kind of reminds me of like a doctor calling death a complication, but one side effect is stopping the program. And so they were developing at the time a language called Sizzle, I'm not sure how it's pronounced, S-I-S-A-L. Anybody here heard of Sizzle? Show of hands. Sizzle? Thank you, Sizzle. So a few people have heard of it. Anybody here heard of Fortran? Okay, I think we know how that worked out. So what's interesting, though, is that a lot of this criticism ended up being incorporated into the standard. So I would actually say that in many ways what they're saying was not just rumors of Fortran's demise, but also a roadmap for Fortran's future. Because a lot of what they were saying we can now do. And that gets to the dream that I had for how to write programs, starting back when I became a professor at the City College of New York in 1999. And what I really wanted to do was to make software representations of partial differential equations more closely resemble their textbook counterparts. One of the issues that I saw, and still see largely today, is that if you look at most codes, and let's say, so I studied mechanical engineering, you took your first class in fluid dynamics, for example, as a junior, and if you took most juniors who just studied fluid dynamics, they just saw the Navier-Stokes equations for the first time, and walked them over to a computer screen, show them a computational fluid dynamics code, they won't find anything on the screen that looks even remotely similar to what they just learned, right? So what I wanted to be able to do is to apply differential operators to continuous mathematical abstractions supported by discrete approximations executing in parallel. And I achieved at least some version of that vision early on, probably as far as 20 years back, but that was just using loop-level parallelism with OpenMP. And what I really want to do now is trying to get this same sort of thing to work in distributed memory, and we have gotten it to work to some extent on at least what I'd say so far are toy problems, and I'm trying to move towards the more complicated problems now to see if we can get this to work in modern Fortran. So we'll talk about two problems. One is a PDE solver, so that'll be my HPC example. And I'll use the symbol delta to represent the HPC problems. So when you see delta, it's something that we use, for example, in finite differences a lot. My preference would be mimetic discretization methods, which Jose Castillo at San Diego State develops. I'm looking forward to getting started on new collaboration with him in that area. And I'll mention there's 2 whole sessions on mimetic discretization methods tomorrow afternoon, so that's where you'll find me. My book focused on object-oriented design patterns. So object-oriented programming is how you write a class in an object-oriented language. Object-oriented design is which classes you choose to write, and design patterns are which classes should you write, basically. What are the relationships between the classes? What are some common classes that people write in a given domain? And so in the book, I talked about something called the abstract calculus pattern, which basically was what I was describing a moment ago, writing differential operators that work on continuous abstractions that are then supported underneath by discrete algorithms working in parallel. So this is a conference sponsored by an applied math organization and conference focused on computational science. I'm betting there's a pretty good fraction of people in the room who know what equation that is. Let's see a show of hands if you know what equation that is on the screen. I'd say that's about at least 35% probably of the room. I would say there's a lot of power in the expressiveness of that fact, that you can recognize what I'm doing before I've even said it. And I would say that that would make a big difference, especially in educational settings, either in teaching or even in grad school, when you're introducing a student to a code for the first time and they're having to come up to speed on it. Imagine how much faster that goes if, in the span of a few seconds or a minute, they see something they recognize, right? But that's actually driving the computation. This is not pseudocode. This is standard conforming Fortran syntax. In Fortran, when you define your own operators, you bracket them with a dot. So that's what you're seeing there. Everybody recognize that as the Navier-Stokes equations, the incompressible form. And importantly, as it ties back into what Backus was after with the functional programming style, as of Fortran 95, you could tell the compiler that your procedure is pure, that it has no side effects, and that ideally it has a unique mapping from inputs to outputs. The language doesn't quite constrain you. There are some ways that you could get around that, not so much in the side effects area, but in the unique mappings. So we're trying to improve that. There's now a new form of function in the language called simple, which moves us a little bit further in that direction towards a true functional programming style. And the next thing I wanted to show didn't come up. So there in amber, each of the entities that I'm showing here can be a distributed object. And this is all just with the language, all the way down. No MPI anywhere in the source code, no OpenMP anywhere in the source code or anything like that. So that's sort of the vision that I'm after. When I mentioned having done it so far on toy problems, I've written, say, the 1D Burgers equation, and we've been able to show that that can scale with 85% parallel efficiency out to something like 16,000 cores. Moving towards 3D problems, we now have a 3D diffusion equation solver that adopts this pattern, and it simulates the motion of T cells in the human body. And the idea is that T cells move with a distribution of speeds and angles, and Matcha, the motility analysis of T-cell histories and activations, the software that we're writing. And they also can communicate with each other. If they find an infection, as they move towards the point of infection, they can secrete soluble mediators. Again, I don't know if I'm getting the pronunciation right here, cytokines and chemokines, and use that to figure out how to get to the point of infection. So we now have this working with some simple discretizations, just using central differences in 3D. As I mentioned, I'd like to move towards mimetic discretizations where we'll have higher orders of accuracy and we'll have discrete forms of the Gauss divergence theorem, for example, or various integral theorems that apply. And this work was done in collaboration with David Torres. He was working in this area before we came together, and we came together through the Sustainable Research Pathways program. And that's a really important theme throughout the work that I'm going to show you, is that David's at Northern New Mexico College, and before we started collaborating, I hadn't heard of Northern New Mexico College. What I really like about Sustainable Research Pathways is that it gets DOE National Lab researchers not just collaborating with the usual suspects, working with people across the spectrum of institutions in academia, faculty, and students. And my collaboration with David has been hugely impactful on my work. As I mentioned, I wasn't working in that area until I met him. So you can see in Matcha, there's an example program that you can run. I have a command that we'll show in a moment if anybody wanted to clone the repository and try running it yourself. So for example, on line 64 there, you can see that we're solving the equation using this style that I just talked about with user-defined operators. And this is all running in parallel using the parallel features that are built into the Fortran, which oftentimes people refer to as co-array Fortrans. You might have heard of that. That's the functional style. Also a more traditional procedural style you can see at line 89, where I'm simply modifying the object that I'm invoking a step procedure to take a step and invoking that on an object that I'm calling T, passing in some data that it needs, and you could clone this and try running it yourself if you have the Fortran package manager installed. If not, see me. It's probably the easiest thing in the world to install. The entire Fortran package manager, every time they do a release, gets concatenated into one file, which is about 45,000 lines now. Compile that one file, and you have a working implementation of the Fortran package manager. So, and hopefully you'll observe that they run in about the same amount of time. So that's one of my goals here, is to try and figure out, can we get this, what I would say more expressive, more clear, functional programming style to execute in a manner that's similar to, in a time that's similar to the more traditional procedural style. So this is an example where I'm just running it in 2 images. That would be analogous to 2 MPI ranks, if you're familiar with MPI. So we've done some analysis on the performance using the Tuning and Analysis Utilities Toolkit, TAO, developed by another collaborator, Samir Shinde at the University of Oregon. And what we find is that at line 188, we have the beginnings of a do concurrent loop. So this is a looping mechanism in Fortran that enables you to communicate to the compiler that there are no data dependencies between passes through your loop, and that they can be executed in any order and potentially in parallel. Again, the language doesn't completely constrain you. There are some things that you could do inside a do concurrent where you wouldn't quite get the right answer, but mostly the language tries to nudge you in the right direction. And one of the ways it does that is by adding a constraint that says that any procedure you call inside of a do concurrent has to be pure. So, the word pure almost makes it sound like we're becoming religious about our programming. In fact, it actually enables something that's really important in a practical sense, which is that we can now parallelize this loop. And we have some examples of parallelizing it with on CPUs with the LLVM Flying Fortran compiler, which my group contributes to. And there are some compilers that can also offload do concurrent to a GPU, which makes it really important, of course, in the AI era. And that should be coming soon in LLVM Flying as well, I think, probably later this year. One big problem. So the world's shortest standard conforming Fortran program is just the keyword end. Unfortunately, when I first started trying to get this approach to work with one compiler, which we'll rename Nameless, this is also the world's shortest standard-conforming bug reproducer. With that particular compiler, if you turn on the features that you need for the SPMD-style parallelism, so the MPI-like parallelism that's in Fortran, and if you also simultaneously turn on the features that you need for automatic offloading to a GPU, this program segfaults. I spent a lot of time submitting bug reports. Since the beginning of 2024, I've averaged about 1 bug report a week on some compiler, but we're getting there. That vendor has told me that they now have an internal version of their compiler that can pass all of the tests in the test suite for at least the next package that I'm going to show you. Unfortunately, I didn't report the bugs to them on Matcha until last month, so they're still working on that. Moving into AI, I'm going to use the symbols epsilon and iota. And because in AI or in deep learning, you're trying to minimize a cost function, we oftentimes use epsilon for things that are small. And iota relating to information theory, and you'll see how that plays in just a moment. As mentioned in the introduction, I developed FIATs. It's the Functional Inference and Training for Surrogates library. Alternatively, you could call it Fortran Inference and Training for Science, because our goal is to support Fortran codes. And we just submitted our first paper on FIATs to a workshop that will happen at ISC in June in Germany, talking about the programming strategies that we're using and how that distinguishes it from the alternatives. So in terms of supporting Fortran in deep learning, there's sort of 2 categories of alternatives that have come around over the last few years. One set of APIs that are basically just Fortran front ends for C++ software. In 2 cases for libtorch, which is the back end for PyTorch, and in 1 case for TensorFlow. And then there are, in a quick literature search, I found 3, including us, native Fortran solutions, where we're doing the deep learning in Fortran all the way down. And one of the reasons we want to do the deep learning in Fortran all the way down is things like what we've been talking about. We can provide pure procedures so that if you're doing inference, the applications that we've been working with so far are primarily in the atmospheric sciences. So, for example, I collaborate with Ethan Gutman at the National Center for Atmospheric Research, NCAR, in Boulder, Colorado. He develops ICAR, the Intermediate Complexity Atmospheric Research Model, and he wants to be able to replace his cloud microphysics model, which basically will tell you at every point in the atmosphere, will liquid or ice water form at this point? So he needs to be able to, if he's going to replace that with a surrogate neural network, he needs to be able to do inference at every grid point, at every time step, in a 3D, unsteady simulation. So obviously that needs to be efficient. If we can make our procedures pure, that means users can call our procedures inside do concurrent. That means their calls to us, to our library, can be automatically parallelized by compilers, and in some cases, automatically offloaded to a GPU. And that's not true for, I guess, of the other 5 that I mentioned, there's one that has pure subroutines. We have pure functions, which is slightly different, partly a style choice, but for the most part, certainly for the C++ APIs, I'm not even sure that would be possible within the confines of the language. Again, I want to highlight David Torres. We started collaborating on Matcha. I was working on FIATs, and we hadn't even decided that we were going to collaborate on FIATs, but as I was developing my backpropagation algorithm, I was at a point where I had a problem. I could train like single layer networks, but anytime I went to a deeper network, my code would crash. Before I could get my code fixed, David handed me a working backpropagation algorithm that he had just developed in his spare time. It's great collaborating with a mathematician. And the way I work with a lot of my collaborators is I say, write code however you see fit. David basically writes Fortran 90. I take it, modernize it, move it to a more functional, object-oriented style, using Fortran's parallel features and what have you. But his contribution is absolutely central and critical. So what does that enable us to do, and how does it relate to the way most people would write code today? This is how you would do inference with our library, how most people would probably write the code. Again, we're working on a 3D grid, so we've got a collection of objects here that I'm just calling the inputs. So that's an object that I'm passing in to this infer procedure that I'm invoking on a neural network object. And I'm writing nested loops. And when you're writing loops, you're telling the these are inherently serial. You're telling the compiler, do these iterations in this order. And that's actually really important, because if you're doing something like time stepping, you need to respect causality, right? So then you come back and say, oops, I lied. I don't really want you to do them in this order. I want you to do them in parallel, which is what you do with a directive that's outside the language. I would say far better to just write something that's parallel from the start. It also happens to be more compact. You also don't have to do things like telling the compiler to collapse the 3 loops, which you see in the OpenMP directive up above, because there is no ordering implied here, even with what looks like 3 nested loops. To take things a little bit further, as of Fortran 95, you could also write something called an elemental procedure. Unfortunately, I don't see these in the wild very much, but the basic idea is that I can write a procedure that looks as if it takes scalar arguments, but then I can decide to pass in arrays. And the compiler will apply that procedure to every element of the array and give me back an array result. That enables me to take what I'm doing and collapse it down to one line, at line 74 at the bottom there. And ideally, I'd like to see compilers parallelizing that. So that line works now with the compilers that we can compile our code with, and unfortunately, they don't parallelize it yet. What I'd say is really significant here is that what you're looking at in that one line is a combination of 3 or 4 different programming paradigms. One, it's an array statement. I talked about that with the elemental procedure. Secondly, the infer function is pure, so it's something that's inspired by functional programming. Thirdly, I'm invoking that procedure on an object, so it's object-oriented programming. And there's no ordering implied between the elements of the arrays that I'm working on, so it's implicitly parallel, like they were talking about in that technical report from 1991. I gave a keynote at the International Fortran Conference a few years back, and the title of my talk was Fortran at the Intersection, because the theme of the talk was how one programming paradigm supports another, sometimes how 2 combine to support a third. This is a literal picture of Fortran at the intersection. Just before I joined Berkeley Lab, Axel Hubel, who's at the lab, spotted me. That's my license plate. I have Fortran on the license plate. And so this is what we get, doing that inference with do concurrent. What's happening is the LLVM Flang compiler is actually translating the do concurrent to OpenMP. And you might think that because it's doing the translating for you, there could be some loss in performance. But in this case, both the do concurrent and the OpenMP are scaled on the serial code, and they get nearly identical performance. This is with a model trained by Zhe Bei at Berkeley Lab, where she trained a neural network as a surrogate for the aerosol dynamics in the energy exascale Earth system model, E3SM, that's developed by the DOE community. Moving on to training neural networks. One of the most challenging problems we've had to deal with, I talked about the cloud microphysics model predicting where liquid or ice water will form. If you step outside, look around, unless it's foggy out, the air is clear all the way up to any clouds and clear above the clouds. And if there are no clouds, it's clear all the way up. So a lot of the data, if you're trying to predict liquid or ice water forming, a lot of the data is basically zeros. We're trying to predict time derivatives, in this case of 5 quantities, 1 on the left and 4 on the right. And these are histograms of these quantities, and what you can see is that they're really steeply peaked around 0, because most of the time there's nothing happening. And so it was really challenging to think about how to get rid of the uninteresting points. Sure, you can throw away the zeros, but this thing spans 8 or 9 decades. So you throw away the zeros and you're left with a bunch of points that are almost zero. You throw away some of those, and you're left with a bunch of points that are almost zero. Ultimately, what I landed on was to try and flatten the histogram, basically by sampling in such a way that we get ultimately a uniform histogram. And at some point, I realized that what I was really doing was maximizing information entropy. And the idea being that, as Shannon defined information entropy, if each outcome is equally probable, then you've retained the maximum amount of information you can in that size data set for the problem that you're working on. What's interesting to me is that I came to this intuitively, and it wasn't until I was reading an article in the Communications of the ACM on a banned topic that I realized, because they were using information entropy on a banned topic, I'm blocking out one of the words that's below the title there, because we've all been told these days that there's certain things we can't talk about. 3 words in particular, that if you're working on those 3 words, you get fired. You're not allowed to do this. So many of us are engaged in what some call anticipatory compliance, self-censorship. I will self-censor, but I want to be clear that I'm doing it, because I want everyone to know that they're missing information. But it was an article on a banned topic that brought me to that point. So why does that matter? I'd say it matters because background matters. And that's what I want to work towards for the rest of the talk. My partner and my son gave me a book for Father's Day a few years back called The Jazz of Physics. When I first saw the title, it seemed backwards. I was used to seeing books about things like the physics of jazz. They'd talk about acoustics and vibrating strings and things like that. This was the reverse. This was Stephen Alexander. He's an African-American cosmologist at Brown University, writing about the fact that he's also a jazz musician. And sometimes when he goes to jam sessions and he's listening to other musicians, his music inspires his physics theories. Now, when you first hear that, at least when I first heard it, maybe even it sounds a little bit hokey, like, come on, really? But then he had a couple of quotes in the book. One is by Abdul Salam, Nobel laureate in physics, who, when Stephen Alexander and Jim Gates, another black physicist, were in grad school at MIT, Salam turned to Jim Gates and said, one day when your people do physics, it will be like jazz. Now, when I first read that, honestly, to me, it came across a little bit patronizing, but the most important thing is they didn't take it that way. And so they interpreted it as sincere, and I will as well. So maybe you're not crazy about that one. Maybe you haven't heard of Abdus Salam. How about Albert Einstein? When he was asked what was the basis for his special theory of relativity, he said, it occurred to me by intuition, and music was the driving force behind that intuition. My discovery was the result of musical perception. So we all bring so many things to our work from other interests that actually can influence our work. And that's one reason that I would say background matters. Stephen Alexander is working from a musical tradition that was started by African Americans. It stands to reason that he might do his physics a little bit differently. I used to write a lot of poetry. I won't subject you to my poetry. But that actually inspires my coding. You hear about mathematicians talk about a proof being elegant. I see a line like that one line combining 4 programming paradigms as elegant. And I'd say that the way I write code, I think of as poetic. I'll give you one thing that maybe comes the closest to some poetry about the code, or at least I hope it comes across poetic. I was inspired by a book by Michael Pollan about the food industry and about food. And the book is entitled In Defense of Food, An Eater's Manifesto. And he had written several books on food at this point, and he was trying to summarize his philosophy in the simplest way. And he said, eat food, not too much, mostly plants. The eat food part probably sounds obvious. What else would you eat but food? But he has a special definition of food. And essentially it's, if your great-great-great-grandparents would not recognize it as food, it's not food. Doritos are not food. Twinkies are not food. They're a manufactured substance. So when I was giving my talk for the International Fortran Conference, and this is my book on the left, I couldn't avoid the one shameless plug there, I came up with write software, not too much, mostly pure functions. And again, I have a special meaning here for software. If you're just writing code, we talk about our code all the time. If you're just writing code, I'm not going to call it software. Do you have unit tests? Do you have those tests running, in a online automatically when people push to your repository? Do you have a Git repository? Documentation. This is all the scaffolding of what I would call scientific software. The not too much part, I love that one line of code. I can show you examples where we can write in one line with careful use of the intrinsic functions in the language and various other features of the language in one line what most people would write in 10 to 15 lines of code. So I'll give you a hint. There's only one word that's being blacked out in this talk, so you only have to figure out what that one word was. It's a bit more about why background matters, and this is about a paradox. And this is a group of researchers in education and computer science. I believe they're at Stanford, if I remember correctly, they looked at a very nearly exhaustive collection of dissertations published in the US from 1977 to 2015, used machine learning. This is back in, 2020. And we're looking for novelty, innovation. And one of the ways that they were measuring that was bringing two concepts from disparate fields into contact with each other. And what they found was really interesting in terms of demographics. The smaller your demographic is at your institution, so for example, women in computer science, if that's a small percentage of who's in computer science at your institution, the more likely you are to do novel work. That's the top right graph. The bottom right graph, unfortunately, shows that the smaller your demographic is in your institution, the less likely it is that someone else will take up the same idea, cite your work, or use the same concept after you. So that missing word matters because it's what gives us better science. This was an article that I saw just as I was headed to give a talk that was touching on one of the banned topics in the New York Times. And this writer was saying, is a gay Republican Latino more capable of conducting a physics experiment than a white progressive heterosexual woman? Would they come to different conclusions based on the same data because of their different backgrounds? For most people, the suggestion isn't just ludicrous, it's offensive. What really gets me here is the word ludicrous, literally ridiculing anyone who disagrees. I'd like to see us bring math to the world, all of these subjects, because my problems with that statement are mathematical. Let's look at it. I would say that science answers questions that scientists ask. Asking different questions might get you different answers. That's probably might seem more obvious to you in the social sciences or humanities, but guess what? We're not so far from the social sciences or humanities. Remember the Communications of the ACM article? That was social science. It inspired a new way of me looking at my work in AI. We're not so far from the humanities. Think of physics of jazz. So I'd say there are two problems with what was said in that article, the quote that I gave. One is more capable implies that there's a metric with which you can write inequalities. Another is that the question starts off with the word is, which implies that there's a single deterministic answer. So what if we reframe that and say, might a gay Republican Latino have different capabilities that could influence how they would conduct a physics experiment, or which experiments they might choose to conduct as compared to a white progressive heterosexual woman? Might clarifies that what we're talking about is probabilistic. We haven't been given enough information to fully determine the answer. Different capabilities qualifies that we're talking about a richer and more complex set of capabilities than just one about which we can write an inequality. And I'd say the answer to that question is yes. I've only got a couple minutes left. I'm no stranger to that kind of ridicule. when I first went to Sandia National Labs, someone asked me what I do, and I mentioned object-oriented programming and Fortran, and his reply was, wow, you must take a lot of abuse. People will write things publicly, like referring to Fortran as the infantile disorder on the left. In the middle, you can write Fortran in any language. That's a lot of software engineers' way of saying you can write bad code in any language. How would it feel if that's your life's work? Fortunately, I think things are changing some. Maybe some people actually are, praising Fortran. I guess one of the last things I want to say is this is from an article where Lois Kerr-McKinney from Argonne National Lab interviewed Marianne Leung and myself and asked about, what inspired our work. And I'm sorry this is too small for you to read from there, but the basic idea that I was saying here is that early on in my career, I think sometimes it's hard for me to remember what all the motivations were. I certainly know that I loved Fortran, but I also think I had a little bit of a rebel in me, and it didn't hurt that I was in Harlem, which is a storied place with so many people who have led social movements. And I think a big part of me didn't want to run with the mainstream, and I think part of that was because I knew I was already outside of the mainstream to begin with. So I think that's why I took up this kind of work. This paper blows me away because, well, at least before the deep learning era, I'd never seen a paper with this many citations, where Kimberly Crenshaw defines intersectionality, or popularized the term. And I don't have enough time to go into the details here, but I just want to say what I eventually realized is that the thing that's the most intersectional about me is not the fact that I'm a Black person in science, it's the fact that I'm a Fortran programmer in computer science. How many of those are there? So, conclusions. Let's get back to the question, what happens to a dream deferred? Sometimes it sags like a heavy burden. Hopefully these slides will become public afterwards since I don't have time to go through everything with you, but this is kind of an analysis of the article, focusing on the word explode at the end of the title. And I'll just say, sometimes it explodes in popularity. Fortran recently got back into the top 10 on the TIOBE index that measures popularity of programming languages. Sometimes it leads to open rebellion, driving around with a Fortran license plate. And most importantly, I'd say background matters. Let's work towards a world where we can bring our whole selves to our work, and where we can bring math to the world in all of these conversations, not just the ones where it's more obvious that math is involved. And we can do that with delta, epsilon, iota. Fortunately, at this conference, everybody knows Greek, or at least the alphabet. I'll put up my future reading list. The one on the right, I haven't read yet, just getting going with the one on the left. And I guess there's only 1 minute left for questions. Sorry.
So you are correct that in 15 minutes the next session starts. If somebody has a very quick question, we'll take it, and otherwise, since I'm not seeing anybody running up behind me to the microphone, let's thank Damien again. And